Hello. Here we'll talk about vector spaces. And linear maps. Well, we just talk about their definitions, but these are the key players of linear algebra, of abstract linear algebra. And everything starts with the domain where we take our coefficients from. That's supposed to be a field. And vector spaces are sort of defined over a chosen field. It makes sense to talk about vector spaces which are over the same field. So a vector space over a field is an abstractly defined vector space over a field is, well, first of all, a set of vectors together with two structures. One is addition, which formally is a binary operation. It takes a pair of vectors and assigns one vector to it, which we call the sum. And then the second operation I will call scaling. And this time it's a binary operation, but the first argument is from our ground field. So what this operation is usually denoted by is a scalar C multiplied by a vector V. These two operations have to satisfy certain properties for capital E to be vector space, and the properties I will list in a slightly unconventional form, minimizing the number of them. So the first two properties are about addition. One is associativity. And it says that if we take any three vectors and form this triple sum in this way, so first sum V and W and then add U, and then add the result to U, it will be the same as if we start with U and take the sum with V and then add W to it. The second property is commutativity, which says that U plus V is the same as V plus U for any vectors. And the next two properties are about two operations simultaneously linking them together. They are colloquially called distributivity property. So one is if we take two scalars C and D, take the sum, multiply by a vector, it will be the same as if we just take C and multiply by this vector and scale V with the other scalar and then take the sum. Or we could take one scalar and two vectors and first compute their sum and then scale it up. And that should be the same as if we scale this vector separately and then take the sum. So the last property which will make it a vector space is the one which says that the zero scalar multiplied with any vector is equal to the zero scalar multiplied with any other vector. So it doesn't matter what I choose as U or V. For all such choices, the result is the same as zero. So that is not what usually listed as a list of axioms in the book. Usually zero vector is, and then I call it the zero vector. Usually zero vector is defined in here as the unique vector which added to any other gives that other summand. And then negation of vectors is axiomatized. But that all comes from the field properties if we just have this property. So that is shorter list of axioms. Speaking about examples, I'll just call it one example, but it will be sort of ramifiable. We will have more examples straight after. Coordinate vector spaces, these will be our main examples. We'll mostly talk about finite dimensional vector spaces. But here I will look at vector spaces which can be arbitrarily large. So the name of this example is f-valued functions. I will look at them as vectors, and the set of them I will denote as a set of maps from something. So I fix a target, call it x, into my ground field f. And so I should separate probably. This is still the definition of my vector space. So that will be my set V, and then I need to define addition and scaling for elements of this V. And if I take two maps, I need to define a sum. That has to be a function on X with values in F again. To define a function, I need to give a way of computing its values on any element in my source X. And here is a rule. Just compute the values of F and G and take the sum. And that is a definition of addition of functions. And the same way we can define the scaling of any function with any scaling coefficient. And it is a function again, and its value on X is the value of F scaled. So these two operations will satisfy all these properties. And that is an exercise, an easy exercise. And varying X, we can have different vector spaces, and if X is not finite, then these vector spaces will be not finite dimensional. And specific choices of X and the ground field allow us to look at interesting subspaces. But let me first define a way of relating different vector spaces. So the way two vector spaces talk to each other is via linear maps. Let U and V be vector spaces over our ground field F. A map from U into V is linear if two properties are satisfied. First, it has to preserve addition. And that is to preserve addition. U and V are arbitrary vectors in the source vector space U. And second, it has to preserve scaling. And that is the exact way it's supposed to preserve scaling. So these two properties are aligned with the structures we have in the vector spaces U and V, and a map with these properties is really a strong relation between these two vector spaces. I will first look at very simple examples, but maybe before I will do that, I will say what for two vector spaces to be isomorphic. A linear map or a bijective linear map is called an isomorphism. And that is for two vector spaces to be roughly the same. Well, really the same. It's just a different way of writing which distinguishes between them, and phi is really a rewriting rule between these two different ways. So for all practical purposes, vector spaces with a bijective linear map between them are identical. And the notation for this situation, if there is a bijective linear map between U and V, the short notation is like that. So these vector spaces are called isomorphic. So one little take-home exercise is the following. If a map is bijective, then it is invertible, then there is the undoing map going another way. So prove that phi inverse is also linear. So having a bijective map one way, its inverse, and having it linear, its inverse will automatically be linear, which is not a part of this definition. So that is that exclamation sign means that this is a delegated question, delegated to you. Now I'll proceed with examples, but now of linear maps between vector spaces. So I will just try to play with these guys, but I will make my choice of x and of f a bit more specific. I will choose f to be the field of real numbers and x to be the same set. So what I will be looking at is the vector space of real valued function of real variable. And here we just have all functions. From R to R. And of course, some of them, or most of them, are really ugly in a sense, say, of analysis of calculus. They are broken, they are just random, the values of neighboring inputs are totally different. But we can look at the subspace of continuous function. And that is really a subspace, so I didn't give a definition of a subspace, but that is a vector space with respect to the same operation. That is a subset, which is a vector space with the same operations as the ambient vector space. So here we just look at continuous functions. So what is for that subset to be a subspace? Well, it has to be closed under addition, and that is a simple statement that the sum of continuous functions is continuous. It has to be closed under scalings again. Zero function has to be in it, and of course the constant zero function is continuous, and the negative to any continuous function has to be continuous, and again it is. So this embedding is a linear map. That is my kind of simple example of a linear map. Then I will look at more subspaces, smaller subspaces. So here, say, I will look at a subspace of functions which are differentiable with the first derivative being continuous. And we could continue this game. We could look at functions which are differentiable infinitely many times. They're called smooth. So all these are nested subspaces, and all those embeddings are linear maps. But they are rather boring, so let's look at somewhat more interesting. Let's again borrow from calculus the operation of taking a derivative. If we look at the smallest subspace of smooth functions, infinitely differentiable, then this operation can be considered as starting and ending in the same set of small functions. So if we differentiate, infinitely differentiable will still be infinitely differentiable. And in this case, we have a statement is that this is a linear map, that it satisfies these two properties. The derivative of a sum of two functions is the sum of their derivatives. Well, that is true. And then the scalars can be pulled through the derivative, and that is true as well. So this is a linear map from a vector space to itself. Such linear maps are called linear operators. To have an example where we start and end in different places, we could use the same prescription for the transformation, but start in a larger, say, in a larger space of just continuous derivative functions with continuous derivatives. And then if we differentiate such a function, we don't necessarily end up with this in the same subspace. We could only be sure that the function, the result, will be continuous. So we have a map going this way. And this is a proper linear map. Alternatively, we could, again borrowing from calculus, define a map going the other way. Which will take a function and transform it into the following function, defined to be the integral of little f, say from 0 to x. A continuous function can be integrated. This Riemann integral is well defined, and moreover this integral is a differentiable function, and moreover its derivative is the original function f. So that's the fundamental theorem of calculus. So we do have a well-defined map from continuous functions to functions with continuous first derivative. These two maps are going just both ways, from C1 to C and then from C to C1. Yeah, are they inverse to each other like in these bijective situations? I will call this second map the integral. Well, that is it. More is to come.